2 months since my last video. I'm sure all 20 of my subscribers have been desperately refreshing their page, waiting, hoping for a new Tesseract video. And to those people, I apologize. I've been busy. Ugh. And apparently I have to apply to colleges or something. But I'm here now, and boy do I have some big updates for you. Well, kinda big. I haven't been able to make videos, and I also haven't been able to work as much on the game as I'd like to. So even though it's been about 8 weeks, I only have a solid 2 weeks of progress to show to you. But it'll be great. If you're new here, my name is Carson, and I'm working on an online multiplayer top-down shooter mobile game. This is the first devlog, but it's actually the second devlog. Check out devlog number 0 if you're interested in the vision I have for the game and the backstory behind it. Yes, I started with 0 because I'm a programmer. Okay, so let's pick up where I left off last time. I have a little soldier, he doesn't have a face, he has a gun, he can shoot the gun, and he can shoot people with the gun. Oh wait, we haven't gotten there yet. He can shoot rocks with the gun. So where did I go from here? Well, we currently have no multiplayer in my multiplayer game, so maybe we should start with that. I used to have multiplayer, but then I deleted it. Let's talk servers for a few seconds. Don't go, it's fun, I promise. In multiplayer games, players somehow need to send their information to all the other players and receive information from all the other players. This is how the game stays in sync across multiple devices at once. There's a few options for this. Some games use a peer-to-peer networking architecture, where every player sends their information to all the other players. If you want to move forward, tell everyone that you moved a few steps up. If you want to shoot someone, tell everyone that you got a hit. That way sucks. Shut up, Destiny. The main problem with this design is cheaters. Cheaters normally aren't a big issue in single-player or co-op games, but in a multiplayer game they can be absolutely detrimental because they affect everyone else's experience. In a peer-to-peer network, there's nothing stopping players from sending fake data to everyone else. That's why the vast majority of competitive multiplayer games these days use an authoritative server architecture. In this model, a server keeps track of the game state. Each player, called a client, sends their inputs to the server, for example what button they are pressing or what direction they are pushing the joystick, and the server updates the game state accordingly. The server then broadcasts the game state to all the other players, so each client has an accurate copy of the game on their own device. Obviously, players can no longer teleport or register false hits because all they can do is tell the server what direction they'd like to move in and when they would like to shoot.
Nope.
This all seems well and good, but nothing comes without a price. It takes time for data to physically travel through the internet. This is called latency. The only people that hate latency more than players are developers. The first problem that arises is input delay. When you send your input to the server, it may take half a second before you receive an update with the response to that input. Unfortunately, this is very noticeable. To get past this issue, the client can predict where it will be based on its own inputs, and then fix any discrepancies in its position when the update from the server arrives. Of course, fixing the client's position is a bit more complicated than it seems, given that the server's position is in the past and the client's position is in the future. This is alleviated by continuously re-simulating the game, starting at the last confirmed position, in order to find a new predicted position. For now, there's one final issue I'll mention. Shooting needs to be authoritative, but by the time our command to fire reaches the server, the other players' positions will be different from what they were when we fired on our device. This means that we could miss on the server, even though it looks like we hit someone on our screen. The solution to this is rewinding the game on the server to the time where the player actually fired before checking for a hit. This is called lag compensation. So all this stuff seems super complicated. That's why, instead of doing it myself, I'm not doing it myself. Before, I was using Photon Unity networking to handle the multiplayer. Because PUN works with a peer-to-peer system, I decided to treat one master client as the authoritative server and use all the other players to keep the master client accountable. But this was a janky solution that I didn't have full confidence in, and it probably would have used too much bandwidth. It also puts all the computing load onto the player's device instead of on a server. Wait, Pause. Why am I obsessing over anti-cheat anyway? Why don't I just use PUN's peer-to-peer system until I release the game and by some miracle have more than 5 players? Well, I almost did that, but it's very difficult to change a game's networking system once the whole codebase has been built around it. So I wanted to do what I could to start development with the best possible foundation. While I was looking for a new solution, I stumbled upon Photon Fusion. It was everything I had hoped for. It worked with Unity, it was free during development, it was built for the dedicated server architecture, and it handled client-side prediction, lag compensation, interpolation, and more automatically. The thing I like most about it is you can play offline in single player without changing any netcode, so that saves a lot of time and hassle, and will make development a lot easier. Well, Fusion was almost everything I had hoped for. There was one small problem. The package is in beta, meaning there are 0 tutorials for it and barely any documentation. That means it took me pretty much an entire week just to get movement synced. I don't even remember the issues I was having. Some were because of my own stupidity, but others were because I didn't have some random option checked, or because I did have a random option checked. Anyway, after a few grueling days of trial and error, looking through outdated samples and begging for help in the Photon Discord, I finally got it working. You can see the server view on top and 2 clients on the bottom. This is with client-side prediction, and this is without. See the input delay? The next thing to do was sync shooting, which I think is working now. This trail of colliders shows the buffer of previous positions that the server stores for the purpose of performing lag-compensated hit detection. When the server is determining whether a player hit their target, it will use the collider that corresponds to the tick when the client actually fired. I also made a rudimentary health and respawn system that will obviously be expanded on later. And at some point I switched to Unity's universal render pipeline, so that's why the graphics look different. Better, hopefully. Next, I wanted to add grenades, since they will be a big part of the game and they were one of the first things I added in my last prototype. The first challenge was creating a trajectory arc. I broke out the old AP Physics notebook and used the projectile equations to calculate a certain number of points along the trajectory. Unity's line renderer decided to be a twisty boy, so to draw the arc I actually used my script to generate a mesh using the points I calculated earlier as vertices. Right now you can throw grenades by pressing the G key, but eventually I'll add a button for it. The grenade can be aimed with the shoot joystick. Then, when the joystick is released, I just spawn a grenade and add the force I was using in my calculations. Math. Isn't that satisfying? I also do a raycast between every point on the trajectory to determine if the throw is valid, so there won't be unexpected bounces off rocks or something. Then I made a little particle effect for the explosion and things were looking pretty good. This is a placeholder effect, even though I spent like all day working on it. Finally, it's time to add bots. The main reason this is a priority is because it makes testing the game a lot easier, since it's kinda hard for me to control 3 characters at once. And also it's a good plan B in case I have 0 players. We can't just have a bunch of zombie ghosts running directly at the player, so let's get some pathfinding going. Remember how it took me 3 months to get pathfinding working when the game was 2D? Well, now it's as easy as this. Yeah, that's literally all you have to do. Now I can find a path to any point on the map, but that's useless unless the bot knows how to pick a point to travel to. Time to make brain. How do you make a computer brain? With a state machine. For now, we'll just have 2 states, roaming and fighting. We'll just need to define how the bot will act in each state, and when it will switch between the states. Roaming is pretty self-explanatory. The bot will just pick random points and travel to them until he encounters an enemy, in which case he will switch to the fighting state. Here's where things get more complicated. Looking at this situation, what position do you think our bot should move to? Assuming all the other players are enemies. I'm going to add health bars so we can better visualize what's going on. Okay, so now you can see that player A has quite a bit more health than us. Therefore, it might be best to avoid a combat situation with this enemy. Maybe we should move into cover so they can't shoot us. Here, we are safe from player A, but unfortunately we are now in player C's line of fire. Okay, what if we moved to a position that was outside of every enemy's line of sight? Now we might consider this point. Better yet, how about we move as far away from every enemy as possible? Well then, we just end up with a bot that runs away constantly, and that wouldn't be very fun. And of course, the goal of the game won't be to stay alive for as long as possible. The bot needs to try to get kills as well. What is the most efficient way to get kills while also staying alive? Well, it really comes down to isolating one player as the target. We can only attack one person at once, so it makes sense to focus on only one enemy and move so that we are safe from everyone else. So, which of these players should the bot target? You might say player B because he is the weakest, meaning we have the most chance of winning a fight against them. In that case, the best position would probably be around here, where we can shoot at our target but are safe from all the other enemies. By going through this thought process, we can actually start to come up with a set of criteria that will help us control the bot's behavior. Let's first talk about how the bot determines who it should target and who its threats are. Take a look at this sample scene. Each enemy has two circles. The red circle shows the player's threat score, and the blue circle shows their target score. The red line points towards our bot's main threat, and the blue line points toward the main target. As we move our player past the edge of this rock, the circles around player A become as big as your mom.
Got him!
This is because that player became a greater threat and also a greater target once they came into our line of sight. Right now, player A is the main threat because it is closer, but watch what happens when we turn player A away from the bot. Now the bot is targeting player A, and its main threat is player B. The assumption here is that a player facing away from the bot is focusing its attention elsewhere. Maybe they are in combat with another player, for example. Similarly, a player that is facing towards the bot is more of a threat because it is already aiming in the bot's direction. The biggest factor in determining threats and targets, however, is health difference. Watch what happens as I decrease the bot's health. The threat score for both enemies becomes much higher, and they become less attractive targets. If I reduce player A's health instead, then, as you might expect, it becomes a much more attractive target and less of a threat. Basically, I'm designing the bot to be a third partier that shoots the weakest players in the back while they are fighting other people and retreats from any enemies that have more health than it does. In other words, a coward. Everyone likes playing against people like that, right?
Where? He's at the top of the porta-fort. He's at the top of the porta-fort, bro.
When in combat, the bot will constantly attempt to retreat from its main threat.
Why are you running? Why are you running?
And move towards its main target. In the ideal position, the bot should be in cover from all its enemies except its main target. You might be wondering, how does the bot weigh all these factors and select a destination? How does the bot know what points are in cover? Meet the environmental query system. With EQS, we can find an optimal destination by querying or questioning the environment. Put simply, we are just going to sample a collection of nearby points in a grid and score them based on the criteria I laid out earlier. The point with the best score will be set as the bot's destination. Let's revisit the first scenario and attempt to figure out an optimal destination algorithmically. To start, the bot will identify its threats and pick a main target. Now, we can use that information in combination with EQS to find our optimal destination. Each of these little circles represents an EQS node. Here's an example of scoring each node based on its distance from the bot. The more red a node is, the higher the score. The more blue a node is, the lower its score. The node with the highest score is colored green. Next, let's find out what points are in cover. To do that, we can do a ray cast from each node to the main threat. If this ray hits something, then we know there's an obstacle blocking that position from the enemy's line of sight, and we can add points to that node's score. Here's the result of that algorithm. You can see that the red nodes correspond to positions that are not in the main threat's line of sight. Now watch what happens when we layer this with our distance scores. The combined EQS gives us the closest point that is also in cover. I'll go ahead and draw the path to this new destination in black. There's a few more layers that we need to add. How about we check if each node is in cover from all enemies, not just the main threat. If we are outside of an enemy's firing range, we are technically in cover, so let's take that into account. Just for good measure, I'll make another layer based on the distance from enemies and add that also into the composite. Okay, now we have a bit of an issue because the bot is just going to run away. How about we fix that by rewarding the nodes that are close to our target? That's better, but we still won't be getting any kills. Finally, we can add points to nodes that are in line of sight with the target. Look at that, we found our optimal destination. At this point, the bot would be safe from all of its biggest threats and in a decent position to attack its main target. Now, the only thing left to do is to have the bot shoot at its main target if it is in line of sight. And voila! We have a rudimentary shooter AI. Oh, and I added some inaccuracy to the bot's shooting because I was tired of being destroyed. Before we can call it a day though, there's one more issue to iron out. Let's jump into a game with the bot. I'm going to call him Charlie from now on. So right now Charlie is relentlessly pursuing me, but watch what happens when I turn to face him. Now he recognizes me as a threat and is just going to run away. The problem with this is, now I can shoot him in the back, and he's never going to get away from me, so really he should fight back in this situation. It is important to note that a player's speed is slower if they are shooting opposite their movement direction. So normally it would be a good idea to try to escape rather than shoot, but obviously that doesn't always work. To fix this, we need to detect what I'm calling critical situations. We can detect this by comparing the distance to safety and our main threat's threat score. So if the bot is in the middle of an open field and its main threat is very threatening, then it will start shooting at the main threat. Now if there is nearby cover, or if the main threat isn't facing the bot or something, then this wouldn't be a critical situation. So now that I've enabled that, you can see that Charlie will start shooting at us instead of letting us continuously shoot him in the back while he runs for his life. Whew, that was a lot of strategizing, but how does this work in practice? Unfortunately, it's kind of hard to tell if any of the systems I added are helping at all, because the bots still don't seem that intelligent. I think this is because the situation changes so quickly that the bots don't have time to move into their optimal position. But when I'm playing against the bots, it does present a nice challenge. And hey, I don't seem intelligent when I'm playing either. And of course, bots will always look dumb when they are playing against themselves because they are programmed to counteract their own strategies. Basically, any advantage that could be gained from strategy will cancel out. Anyway, the bot's behavior will get a lot more complex and interesting when I add stuff like dashing, team play, grenades, and weapon switching. This will certainly do for now though. So there you have it, you guys are all caught up. I have a feeling I went into way too much detail describing this stuff, but I find it interesting. And if you're still here, then you probably find it interesting too. We pretty much have all the complicated foundational stuff in place, so everything should be smooth sailing from here on out. We're also all caught up with my old prototype, except everything is 10 times better, so that's exciting. Now I can finally work on stuff like the UI, player controls, and weapon switching. With weapon switching comes shotguns, so I can't wait for that. Remember to subscribe if you want to stay up to date with the game, and like the video if you want to help me out. Besides that, see you next time. Hopefully in less than 5 months.